Hello everyone, this is lecture 22, the dot product of two vectors in Rn. So in this lecture, we're going to look at different properties of a vector. More specifically, we're going to learn how to calculate the length or the magnitude, or in general term, the norm of a vector. We're going to calculate the dot product between two vectors and later learn the relationship between the angle formed by the two vectors. And then at the end, we're going to familiarize ourselves with the properties of the dot product of two vectors. So first of all, I'm going to write down the magnitude or the length of the vector. So if you have a vector with the entry of v1, v2 up to vn, so is a vector in Rn, then the norm, even though I say the norm of a vector, when you see the norm of a vector for our course or in this context, you can think of it as the length of the vector or the magnitude of the vector, right? Or length of v or magnitude of v, denoted as you have two vertical lines on each side of the vector, right, to indicate this is the length of the vector, this is the magnitude of the vector, or the norm of the vector, and is defined. So it is defined as. So the length of the vectors is equal to the square root of each component of the vector square and then add them together, or the sum of each component square. Right, so that's how you calculate the length of the given vector in Rn. So you can do this in any dimensions. For the two dimensions, you can do that the magnitude or the length of the vector v in this case is equal to the square root of v1 square plus v2 square, given that v1 and v2 are the components of the vector v. Right? You can do this in three dimensions, of course. The magnitude or the length or the norm of the vectors is equal to the square root of v1 square plus v2 square plus v3 square, given that v1, v2, v3 are the components of the vector in R3. Now, more specifically, let's take a look at the vector of the form -3, 2, 1. If you calculate the norm of the vector, again, in our context, this is the length or the magnitude of the vector. So when you calculate the norm of the vector, you have that this is equal to square root of -3 square plus 2 square plus 1 square. And this is equal to 9 plus 4 plus 1, and this is equal to square root of 14. So because this is the magnitude or the length, the answer has to be in the positive number. All right, so very quick, right? It's very easy to do the calculations related to the norm or the length of a vector. Now we're going to move on to some property of the length of a vector. So if v is a vector in Rn and you have a scalar k, then you have the following properties that, because when you calculate the norm, again, the norm of a vector, the length or the magnitude, when you're talking about the length has to be either 0 or positive. Right? So the first property here is that the length of the vector is greater than or equal to 0. Right? Again, the explanation is that the length of a vector is either 0 or positive. The second property is that when the length is equal to 0, the only case that is going to happen is when the vector of consideration is a 0 vector. Right? So the norm or the length of the vector equal to 0 if and only if the vector itself is a 0 vector. So the length of a vector is 0 if and only if the vector of consideration is the 0 vector. All right, so that's the second property. The third property is that when you want to take the magnitude or the length of the scalar multiple of the vector, this is equivalent to calculating the absolute value of the scalar. The scalar can be negative number as well, right? Multiplied with the magnitude of the original vector v. Right? So in this case, this term is the absolute value of k. Right. Again, because when you calculate the length has to be either 0 or positive number, right? So that's why when you have when you involve a scalar, the scalar can be negative, but you don't want negative for your length or magnitude, so therefore you have to put in the absolute value for the scalar. Now we're going to move on to another definition. You have seen this. I mentioned this definition a few times already throughout the last few lecture notes, but this is the first time that we kind of formally introduce the idea of the unit vectors. All right. So the unit vector is the vector that can be normalized using the norm or the magnitude, right? So for any non-zero vector v in Rn, the unit vector of v is that of u equal to the vector v divided by the magnitude of v. All right, so that's very straightforward. So I'm going to name this equation star. I'm going to use that star a little bit later. Because it's called the unit vector, the length of the unit vector of any unit vector is always equal to 1. Right? So the length of u is equal to 1. Right? So this say that the length or magnitude of unit vector is always equal to 1. Right? Because now for the second bullet point, because you use vector v to calculate the unit vector u, the vector u, the result of the vector u, has the same direction as the vector v. So there is the second conclusion that we can draw. So u has the same direction as the vector v. Right? And the process of calculating the unit vector or this particular calculation of this equation is called normalization process. Right? So equation star is called normalizations. In example 2, we're going to calculate the unit vector of the vector v, right? Again, when you calculate the unit vector has the same direction as the vector consideration. All right, so the vector consideration is vector v, 1, 2. To calculate the unit vector, or the unit vector of the same direction as v, you need to calculate the magnitude or the length of the vector v. So for vector v, the length of the vector v is equal to the square root of 1 square plus 2 square. So this is equal to square root of, square root of 1 plus 4 is equal to square root of 5. The unit vector of v is calculated as, the unit vector of v is calculated as, so vector u is equal to v divided by the magnitude of v. So for vector v is equal to 1, 2 divided by the norm or the length of v equal to square root of 5, or I can write this as 1 over square root of 5 times 1, 2 equal to 1 over square root of 5, 2 over square root of 5. Okay, so the unit vector is of this form, right? 1 over square root of 5, 2 over square root of 5. And again, if you want, you can double check that the length of the unit vector is always going to be equal to 1, right? If you do the calculation for this particular unit vector, you can see that the length is equal to 1. All right, now that is the unit vector. Now we're going to move on to the standard unit vectors. Again, you have heard about the standard unit vectors the last few lecture notes. So now we're going to look at that in more details in this lecture note, not only for the 2-dimensional case, 3-dimensional case, but for the n-dimensional case. All right, for the standard unit vector, standard unit vectors are unit vectors. Right? When you talk about unit vectors, for the 2-dimensional case, you have the notation is I hat. To indicate that is the standard unit vector in the x directions, and j hat is, or in this case, you don't see the hat, but we will write down the notation a little bit later. So I hat is the unit vector in the x direction, j hat is the standard unit vector in the y directions. Okay. And if you have, when you put in the extra directions or this extra coordinate, in this case, in the z directions, k hat is the standard unit vector. Okay, but let me finish writing down the definition here. The standard unit vectors are unit vector in the positive direction of the coordinate axis. Okay. So again, for the 2-dimensional case, you have x directions and y direction, or x coordinate or y coordinate. I hat is the standard unit vectors in the x direction. J hat is the standard unit vector in the y directions. It depends on the textbook that you're reading. Sometimes people have slightly different notations to indicate the standard unit vector. In this case, you can see the pictures give us just the bold I, but when you're writing, doing this in writing, it's hard to just have the bold letters. So that's why I use I hat to indicate that is the standard unit vector. In the x direction is equal to 1, 0, or you can do 0, 1, 0. Right. So this one is the row vector, this one is the column vector. Now for the standard unit vector in the y directions, you have j hat equal to 0, 1, or it can be written in this form, right? 0, 1. So either one is fine. You can use the row vector or the column vector. It doesn't matter which one you use. I mean, it depends on the context of the problem. Now, in the three-dimensional case, you have standard unit vectors in the form of I hat, j hat, and k hat. Right. So for I hat, you have that I hat equal to 1, 0, 0, or you can write in the column vector form 1, 0, 0 like this. For the standard unit vector in the y direction, you have j hat equal to 0, 1, 0, or you do 0, 1, 0. And for the z-axis, you have k hat equal to 0, 0, 1, or okay, so that. Right, so these are the standard unit vectors in 2 dimensions and in 3 dimensions. Now, what about the standard unit vector in the in Rn, right? So in the n-dimensional case. So standard unit vectors in Rn is defined as, so in Rn we no longer use ijk, right, because we're going to run out of letter very quickly. So what we do is that for the standard unit vectors in Rn, you use e1 hat, e2 hat, e3 hat, so on and so forth up to en hat. Right, so e1 hat is the standard unit vector in one direction, in the first direction, or in the first coordinate, or whatever the first coordinate you're considering. Right, in this case, you have n entries. Right. Now, e2 hat is equal to 0, 1, 0, 0, and you do this up to en hat. And from here, you can use the standard unit vector to write a vector in terms of the linear combinations of standard unit vectors. For instance, if you consider the vector v of the form v1, v2 up to vn, this can be written as the linear combinations of v1 times e1 hat plus v2 times e2 hat up to vn times en hat. Right? It's very convenient for us to write a vector in terms of a standard unit vector or as a linear combination of standard unit vectors. All right, so let's do that in example 3. The question is, can you describe the following vectors in terms of standard unit vectors? So for the first part, is a 2-dimensional vectors. So therefore, you write this in terms of standard unit vectors I and j, right? Because this is just 2-dimensional, so I'm going to use I and j instead. So v is equal to 4 times I hat plus 5 times j hat. If you want, you can break the vector down to 4, 0 plus 0, 5. Let me delete this for now. And then you take out 4 and you're left with 4 times 1, 0. And then for the second vector, you take out 5. And you're left with 5 times 0, 1. So this is clearly 4 I hat plus 5 j hat. Now we're going to do the same thing for the 3-dimensional case. The vector v is of the form 2, -3, and 4. If it is written in terms of the standard unit vectors, you have 2 I hat minus 3 j hat plus 4 k hat. Okay. Now we're going to move, so that's 2-dimensional and 3-dimensional vectors. When you move on to higher dimensional vectors, it's convenient for us to use e1 hat, e2 hat, e3 hat, so on and so forth. So in this case, in problem C, this is the 4-dimensional vectors. You have 7 e1 hat plus 3 e2 hat minus 4 times e3 hat plus 5 times e4 hat. Okay. And for the last problem, it's also 4-dimensional vectors. This is equivalent to negative e1 hat plus 2 times e2 hat minus 4 times e3 hat plus 2 times e4 hat. Okay. So up to this point, we are introduced different concepts, including the norm or the length or the magnitude of a vector. We learned how to calculate the unit vector of a given vector, of a non-zero vector. You hopefully understand the standard unit vectors in R2, in R3, and in Rn. Now, the next topic is going to be the dot product and the properties related to the dot product. So the dot product measures the angle formed by the two vectors. You will see in a minute why that is the case. So here's the definitions of the dot product. So if U and V are non-zero vectors of the same sign. So of the same sign meaning that it has to be, they are both has to be two-dimensional vectors, or they have both to be three-dimensional vector or n-dimensional vector. And if theta is the angle between the two vectors, then the dot product of u and v is defined as. So the dot product, the notation is u dot with v. So you have to clearly point out the dot product right here. So dot right here is the dot product. Is equal to the magnitude of u times the magnitude of v times the cosine between the two angles. Right. So when you do these calculations, the length of u or the magnitude of u is equal to a number, the length of v or the magnitude of v is equal to a number, and cosine of an angle is also equal to a number. So therefore, on the right-hand side, the result is a number, right? Or a scalar for that matter. Therefore, there's another name for dot product. It's called a scalar product, right? So you can see the name right here. So right here is also called the scalar product. Later on in the next lecture, we will consider, we will look at different product between the two vectors. It's called the cross product. For that particular product, the cross product, the result is going to be a vector. So therefore, this is another name for the cross product. It's called the vector product. In this case, the dot product give you a number or a scalar. Therefore, there's another name for dot product. It's called the scalar product. And depends on the result of the dot product, you can see something about the type of angle between the two vectors. So if u dot with v is greater than 0, it's a positive number, then you have that the angle between the two vectors is an acute angle. Right. Now, if the dot product between the two vectors is less than 0, so if u dot with v less than 0, then theta is an obtuse angle. And if the dot product equal to 0, right, then the angle is the right angle, or the two vectors form a 90-degree angle, or the two vectors are perpendicular. Then theta is a right angle, or you can say that u and v are perpendicular. Now, there's another name for perpendicular in linear algebra. It's called orthogonal. Right. So these are the three special cases to look at the angle between the two vectors. Depends on the value of the dot product that you get. Again, when the dot product is positive, the angle between the two vectors is an acute angle. When the dot product is less than 0, the angle theta is an obtuse angle. And when the dot product is equal to 0, then the angle is the 90-degree angle, or u and v are perpendicular to one another. So when you do this kind of calculations, the angle between the two vectors is only considered between 0 degree and a 180 degree. I just want to be clear on that. Or in gradient notations, between 0 and pi. Okay. So in this case, you have these pictures. So the first picture show you that is an acute angle. In this case, the dot product is a positive number. So u dot with v is greater than 0. Now in the second picture, this is an obtuse angle. So therefore, u dot with v is less than 0. Now this is a very specific angle. This u and v form a 180-degree angle. So therefore, you have u dot with v is equal to -1. Right? And here u and v form a 0-degree angle. So therefore, you have u dot with v equal to +1. Again, it depends on the situations that you have a different value for the dot product. Can be equal to 0, -1, +1, or most of the time, the three main values that you're going to obtain is either positive number, negative number, or equal to 0. And the angle of consideration is between 0 and 180 degree only. Okay. Now, in practice, most of the time, we're going to use the following formula to calculate the dot product between two vectors. Okay, so if u equal to u1, u2 up to un, and v equal to v1, v2 up to vn, then the dot product of u and v is calculated as, right, you have u dot with v equal to u1, u2 up to un dot with v1, v2 up to vn. Right. So the answer is going to be, so each component, you multiply them together and then add the result at the end. So the first component u1 multiply with v1, the second component u2 times v2, so on and so forth, and then you add all the results together, and that's how you calculate the dot product between two vectors practically. So u1 times v1 plus u2 times v2 plus u3 times v3, so on and so forth up to un times vn. All right. So now let's take a look at the following calculations. So in example 4, you have two vectors. One is in row vectors and part B in column vectors. We're going to perform the dot product of the two vectors. So u dot with v is equal to 3, 5, 2 dot with negative 1, 3, 0. That is equal to 3 times negative 1 plus 5 times 3 plus 2 times 0. So this gives me negative 3 plus 15 plus 0 equal to positive 12. So because it's a positive number, the angle between the two vectors is going to be going to be an acute angle. All right. Now moving on to part B or problem B, the dot product between two vectors is that of 1, 2, negative 3, dot with negative 3, 5, 2, and you have that 1 times negative 3 plus 2 times 5 plus negative 3 times 2. And if you do the calculations correctly, the answer is going to be equal to positive 1. So now let's move on to other problems. Now we're going to do some mix and match calculations where you have the dot product involved. Right. So given the three vectors u, v, and w, in problem A, you want to do the dot product first, and then whatever results you got, you multiply with the vector w. Okay, so for this calculations, I have the vector of the form 1, 2, negative 3, dot with 0, 2, 4, and then multiply with 5, negative 1, 3. So I perform the dot product first, and I'm going to get 1 times 0 plus 2 times 2 plus negative 3 times 4. Then I multiply, just the regular multiplications of 5, negative 1, 3. And for the calculation inside the parentheses, if you do the calculations correctly, you get negative 8 multiply with 5, negative 1, 3. Right, so negative 8 in this case is going to be a scalar, right? And you scale the vector 5, negative 1, 3. So I get negative 40, positive 8, and negative 24. So that's how you calculate the value of u dot with v and then multiply with w. So you follow the structure that you learned in algebra. That if perform the calculation inside the parenthesis first and then multiply that with another vector later. So for problem B, here you have u dot with 2 times w. So I'm going to perform the calculation into parentheses first. So I do a 2 times w, and then later on I'm going to dot that with u. So the vector u is equal to 1, 2, negative 3. That with 2 times w. W is 5, negative 1, 3. So now I have 1, 2, negative 3. That with the vector, the new vector of the form 10, negative 2, 6. Now I perform the dot product, and I get 1 times 10 plus 2 times negative 2 plus negative 3 times 6 is equal to 10 minus 4 minus 18 equal to negative 12. So that's some quick calculations on the dot product. The next thing we're going to look at is we're going to look at the properties of the dot product. Theorem 1, the first theorem of the properties of the dot product is that let's consider three different vectors, u, v, and w, and you have a scalar. So the first property is called the symmetry property, or rather the commutative property. Commutative property. You have u dot with v is equal to v dot with u. So it doesn't matter which directions you do the dot product, the result has to be the same. The next property is the distributive property. You have u dot with v plus w. It's just the regular distributions or regular multiplications here. U dot with v plus u dot with w. Right. So u dot with v plus u dot with w. Okay. Now, the next one is called homogeneity property, but rather is just a scalar of the dot product, right? So if you have a scalar alpha and you multiply with the dot product u dot with v, it's going to be equivalent to doing the scale on u first and then dot with v, or you do the scale on v first and then dot it with u. It doesn't matter which one you do, the result has to be the same. Next one is called the positive property. If you do u dot with itself, you obtain the norm or the length square of u. It has to be greater than or equal to 0, and the dot product of u with itself is equal to 0 if and only if the vector of consideration is equal to the 0 vector. So now I'm going to have some more properties of dot product for us to consider. So if u dot with 0 vector is equal to 0 vector dot with u, and it has to be equal to 0, so just 0 scalar. So when you do distributions, as you can see in property 2 here, distributed property, you can see that the vector u is on the left of the parentheses. Now, what if you have u on the right of the parentheses? Is going to be equivalent to what we see earlier. That is v dot with u plus w dot with u, right? But because u, the dot product is symmetry or commutative, you can write that u dot with v plus u dot with w. Now for the subtractions, right, or the difference between two vectors, u dot with v minus w is equal to u dot with v minus u dot with w. Right? And if u vector u or the dot product is performed on the left, u is on the left, on the right hand side of the difference. Right? So v minus w dot with u is equal to v dot with u minus w dot with u. Again, the dot product is symmetry or commutative, so the result is u dot with v minus u dot with w. Right, so it only works for the dot product, a scalar product. It's not going to work for the cross product, and you will see that in the next lecture. We're gonna utilize different properties of the dot product to perform the following calculations. For this example 6, you're going to perform the dot product for the expressions of u minus 2v dot with its dot with u. So u minus 2v dot with u just give you u dot with u minus 2v dot with u. Okay, so what I did is I used distributed property. Right. Now for this particular calculation, u dot with itself is going to give you the norm of a vector u square, and I'm going to break for the second term. I'm going to break the parentheses. We don't need that after all. Right, so that's the result. So this is a good type of questions to have in the homework or in the test, because you could give you one expression and I want you to show what is the expression is going to be equal to. So this is a good one to practice the different properties of the dot product. All right. So now let's move on to another calculation. In example 7, I want you to perform the dot product of vector u minus vector v, the norm of that square. So I have u minus v squared. So this is equal to u minus v dot with u minus v. Okay. Now from this dot product, I'm going to do the distribute. I'm going to use distributive property. I'm going to do u dot with u minus u dot with v minus v dot with u plus v dot with itself. Right. So what I did is that basically I do u dot with u dot with v, and then v dot with u and v dot with itself. Okay, and also you have to mind the sign as well, positive or negative sign. Now move on to the next one. U dot with itself is going to give you the magnitude of u squared minus u dot with v minus v dot with u, but the dot product is commutative. Therefore, you can write that as u dot with v. And then for the last term is the magnitude of v squared. Okay. Now for the middle two terms, they are like terms, so you can combine them together, and you get u magnitude of u squared minus 2 times u dot with v plus the magnitude of v squared. Okay. Now for example 8, I'm going to do the same thing. You have two expressions dot with one another, and you're going to use distributive property. So I get that is u dot with 3u plus u dot with 4v minus 2v dot with 3u minus 2v dot with 4v. Now, after the expansion or the distribution, what I'm going to do is u dot with 3u is going to be equivalent to 3 times u dot with itself. So basically, I just pull out a scalar in front. Similarly, for this case, I'm going to pull out the 4 in front, and I get 4 times u dot with v. And here on the third term, I have 2 times 3 is positive 6 with a negative in front, so negative 6 times v dot with u, minus for the last term, 2 times 4 is 8, and then you have v dot with itself. Okay, now I'm going to simplify out my calculations further. So u dot with itself is going to give me the magnitude of u squared. And the last terms here, v dot with itself is going to give me the magnitude of v squared. And for the middle two term, again, the dot product is commutative. So you get 4 times u dot with v minus 6 times u dot with v. The final answer is minus 2u dot with v minus 8 times the magnitude of v squared. All right, so that's it for me for this lecture. In this lecture, we look at the one of the two product of two vectors. That is the dot product. Right? The dot product gives us the idea of what is going to be the angle between the two vectors. So in this lecture, we also learn how to calculate the length or the magnitude of a vector, how to both calculate the unit vectors. Hopefully you understand the concept of the standard unit vectors. And we also look at the different properties of dot product and utilize that to manipulate the calculation of the dot products. So that's it for me. Please let me know if you have any questions. Thank you.